Welcome to the lecture on job sequencing and replacement theory module 2. In this module, we will discuss type 3 job sequencing problem, that is processing of n jobs through m machines. This type 3 job sequencing problem is in fact a generalization of type 2 job sequencing problem. We will also discuss type 4 job sequencing problem, that is processing of 2 jobs through m machines. To solve this type of problem, we will take help of graphical method. Let us start our discussion on type 3 job sequencing problem, that is processing of n jobs through m machines. N jobs and m machine problem can be considered as a generalization of n jobs and 3 machine problem. Though we may not get accurate solution by generalizing the procedure of n jobs and 3 machine problem to n jobs and m machine problem, we may get a solution which is nearer to the optimal solution. Let there be n jobs, each of which to be processed through m machines, say m1, m2 up to mm in the order m1, m2, mm. The list of jobs with their processing times is given in the following table. There are n jobs 1, 2, 3 up to n, and processing time on machine m1, m2, m3 up to mn are shown in this table. An optimal solution to this problem can be obtained if either or both the following conditions hold. Condition 1, minimum T1j is greater than or equal to maximum Tij for I equal to 2, 3 up to m minus 1. Condition 2, minimum of Tmj is greater than or equal to maximum of Tij for I equal to 2, 3 up to m minus 1. Now, we develop an optimal sequence algorithm by which we will try to solve this problem. In step 1, we will find minimum of T1j, minimum of Tmj and maximum of each of T2j, T3j and Tm minus 1j for all j equal to 1 to up to n. Then in step 2, we will check the following: minimum of T1j is greater than or equal to maximum of Tij for I equal to 2, 3 up to m minus 1, and a minimum of Tmj is greater than or equal to maximum of Tij for I equal to 2, 3 up to m minus 1. And if these inequalities are not satisfied, then the method fails. Otherwise, we will go to the next step. We will convert the m machine problem into a 2 machine problem by introducing 2 fictitious machines G and H with processing times such that Tgj equal to T1j plus T2j plus dot 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 Tm minus 1j and Tij equal to T2j plus T3j plus dot 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 plus Tmj. We then determine the optimal sequence for n jobs and 2 machines equivalent sequencing problem with the prescribed order GH in the same way as discussed earlier. The resulting sequence will be optimum for the given problem then. Here one thing is to be noticed, that in addition to conditions given in step 2, if T1j plus T2j plus dot 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 Tm minus 1j is equal to C is a fixed positive constant for all j equal to 1 to up to n, then we have to determine the optimal sequence for n jobs and 2 machines M1 and MM in the order M1 MM by using the optimal sequence algorithm. In addition to the conditions given in step 2, if T1j equal to Tmj and Tgj equal to Tij for j equal to 1 to up to n, then there will be factorial n optimal sequences, and each of which will yield minimum total elapsed time. The above mentioned procedure of solving sequence problem is not a general procedure. The method is applicable only to those sequencing problems in which the minimum cost or time of processing the jobs through first and or last machine is greater than or equal to the cost or time of processing the jobs through middle machines. There are many industrial operations in which the machines are set in some order which does not follow this rule. Now, we will take an example and see how the developed algorithm can be applied to find the optimal sequence. We have 4 jobs, each of which has to go through the machines Mj, where j equal to 1 to up to 6, that is there are 6 machines, and we have to process these 4 jobs in the order M1, M2 up to M6. Processing times in hours are given in this table. So, we have to determine a sequence of these 4 jobs that minimize the total elapsed time. Here we first check the conditions which are needed for application of the algorithm. Here minimum of T1j equal to 11 and minimum of T6j equal to 12, maximum of T2j, T3j, T4j and T5j are 8, 9, 6 and 10 respectively. Therefore, the conditions minimum of T1j is greater than or equal to maximum of Tij for I equal to 2, 3 up to m minus 1, and minimum of T6j greater than or equal to maximum of Tij for I equal to 2, 3 up to m minus 1, j equal to 1, 2, 3, 4, 5 and 6 are satisfied here. Therefore, we can write the given problem by converting into a problem where we will consider 2 fictitious machines G and H, and we have 4 jobs A, B, C and D. The processing times on machine G and H are shown in this table. Then using the optimal sequence algorithm which we have already developed, the optimal sequence can be obtained as C, A, B and D. Based on this optimal sequence, the total minimum elapsed time can be obtained from this table, and as you can see, the minimum total elapsed time is 112 hours. Now, we consider another example. Find an optimal sequence for the following problems of 4 jobs and 5 machines when passing is not allowed. Its processing time in hours is given below. we have to find the total elapsed time. Here we see that minimum of T1j equal to 3 and minimum of T5j equal to 6, maximum of T2j, T3j, T4j are 6, 5 and 6 respectively. And the condition minimum of T1j greater than equal to maximum of Tij is not satisfied here, but the condition minimum of T5j greater than equal to maximum Tij for I equal to 2, 3, 4 is satisfied here. Therefore, we can apply the algorithm to find the solution of the problem. Considering the two dummy machines G and H and proceeding as before, we can find the optimal sequence as A, C, B, D. The total minimum elapsed time can be obtained similarly. Here the total elapsed time is 51 hours and the idle time for machines M1, M2, M3, M4 and M5 are 25, 33, 37 and 18 hours respectively. We will now consider another example. Solve the following sequencing problem giving an optimal solution when passing is not allowed. Here we have 4 machines and 5 jobs, and we have to find the total elapsed time for this problem. We see that minimum of T1j equal to 9 here and minimum of T4j equal to 8, maximum of T2j, T3j are 6 and 8 respectively. Since both the conditions minimum of T1j is greater than equal to maximum of Tij for I equal to 2, 3 and minimum of T4j is greater than equal to maximum of Tij for I equal to 2, 3 are satisfied. Therefore, the given problem can be converted into a 5 jobs and 2 machine problem. Further, we notice that T2j plus T3j equal to 10, a fixed constant for all j equal to 1 to up to 5. Thus, the given problem is reduced to a problem of solving 5 jobs through 2 machines, and those machines are M1 and M4 in the order M1, M4. This means that the machines M2 and M3 will have no impact on the optimal sequence of the problem. The processing times of 5 jobs on machine M1 and M4 is as follows. Jobs A, B, C, D and E and machine M1 and M4, their processing times are the processing times already given. So, then following the algorithm, we find the optimal sequence as C, A, E, D and B. The total minimum elapsed time is obtained from the following table, which is 84 hours, and the idle time for machines M1, M2, M3, M4 and M5 is 18, 64, 54 and 28 hours respectively. We were discussing type 3 job sequencing problems, and to solve this type of problem, we have developed some optimal sequence algorithm, and we have seen that this algorithm is applicable only when the processing times of first and or last machine is greater than or equal to the processing times of jobs on the middle machines. So, there are many industrial operations where machines are set in some order which does not follow this rule. So, this algorithm cannot be applied in general, and therefore, this algorithm cannot be applied to type 3 job sequencing problem always to find the optimal job sequence. We now proceed to solve type 4 job sequencing problem, that is processing of 2 jobs through M machines. Problems under this category can be solved with the help of graphical method. The graphical method is explained with the help of the following example. 2 jobs are to be performed on 5 machines, say A, B, C, D and E, and the processing times are given in the following table. Job 1's processing times on machine A, B, C, D are 3, 4, 2, 6 and 2 respectively, and job 2's processing time on machine B, C, A, D, E are 5, 4, 3, 2 and 6 respectively. To solve this problem, following steps are to be followed. In the first step, we will draw 2 perpendicular lines. The horizontal line represents the processing time for job 1, while job 2 remains idle, and the vertical line represents processing time for job 2, while job 1 remains idle. Any inclined line shows the processing of 2 jobs simultaneously. We then mark the processing times of job 1 and job 2 on the horizontal and vertical lines respectively according to the given order of machines. We then draw the rectangular blocks by pairing the same machines as shown in the figure. In the figure, the horizontal line indicates the processing times for job 1, and in the horizontal line we mark the processing time according to the technological order of jobs A, B, C, D and E. We mark on this line the processing times on machine A, machine B, machine C, machine D and machine E. Similarly, we mark on the vertical line which indicates the processing times of job 2, and we mark according to the sequence B, C, A, D and E. Then we draw the rectangular blocks by pairing the same machines. So, we have 5 blocks as shown in the figure, block A, B, C, D and E. Now, our job is to find the minimum time required to finish both the jobs in the given order of machine. Hence, we have to follow the inclined path, preferably a line inclined at 45 degree. While drawing the inclined line, care must be taken to see that it will not pass through the region indicating the machining of other job. That is, the inclined line should not pass through the blocks already constructed. After drawing the line, the total time taken equals to time required for processing plus idle time for the job, and the sum of processing time plus idle time for both the jobs must be the same. Now, avoiding the rectangular blocks, we draw the line starting from origin 0 to the end point or finishing point, moving horizontally, vertically and diagonally along a line which makes an angle 45 degree with the horizontal line. Then the optimum path is the path which minimizes the idle time for both the jobs. So, it is the path on which diagonal movement is maximum. That means, we will try to move in an inclined path rather than horizontally or vertically. And the figure shows that we start from the origin O and then we have to reach to the finish point, but that we can do by moving horizontally or vertically. But since if we move horizontally and vertically, it will not give the optimum path, we will first follow the inclined path and then we move little bit vertically to the upper left corner of the block B, and from there we again follow the inclined path, making an angle 45 degree with the horizontal line, and then the arrow shows the path of our movement, and then we have to again move vertically little bit, and then finally we will move in the inclined line to reach a point where we have to again move horizontally to reach to the finish point. So, here we try to move in the inclined path as much as possible in order to reduce the idle time for both the machine. The elapsed time is obtained by adding the idle time for either job to the processing time for that job. For this example, the idle time for job 1 is 2 plus 3 equal to 5 hours, and idle time for job 1 is obtained if we move vertically. So, from the figure we can easily check the idle time for job 1. Similarly, the idle time for job 2 can be obtained when we move horizontally. The elapsed time equal to process time for job 1, idle time for job 1, which is equal to 22 hours here, and the elapsed time is equal to process time of job 2 plus idle time for job 2, which is equal to 22 hours again. Since both the elapsed times are same, so we get the optimal solution here. Let us take another example. Use graphical method to minimize the time needed to process the following jobs on machines shown below. That is, for each machine, find the job which should be done first and also calculate the total time needed to complete both the jobs. The sequence for job 1 and the sequence for job 2 are shown in this table, as well as the processing time on machines A, B, C, D, E for job 1 and the processing time for machines C, A, D, E, B for job 2 are also shown in the table. Now, following the algorithm, we can draw the path. As you can see, we have 5 blocks here A, B, C, D and E, and we draw the path. First we start with the inclined along the inclined line, and then we follow vertically, and then finally we move in an inclined path to reach to the finish point. Here we have taken care that while we are drawing the path, neither of the blocks is intersected, and we can move in the inclined path as much as possible to get the optimal path. The optimal path is one that minimizes the idle time for job 1. Similarly, an optimal path is one that minimizes idle time for job 2. So, we choose such a path on which diagonal movement is as much as possible. The elapsed time is obtained by adding the idle time for either of the job to the processing time for that job. In this problem, the idle time for the chosen path is seen as 3 hours for job 1 and 0 for job 2. Thus, the total elapsed time is 17 plus 3 equal to 20 hours. In this module, we have discussed type 3 and type 4 job sequencing problems. To solve type 3 job sequencing problem, we have designed an algorithm, and we have noticed that following this algorithm, we can find only an near optimal solution, but we are unable to get always the optimal solution. Further, this algorithm is applicable under some restricted conditions. While in solving type 4 job sequencing problem, we use the graphical method, which usually gives good solution, even though we are not getting the optimal solution always. With these comments, we end this module.